Okay, so today we'll finish up section 3.1 and we'll start 4.1. All right, so first thing I'm going to start off with is some different formulas. Okay, and we talked yesterday about inverse sine and regular sine and how they basically undo each other. Okay, well, what I didn't say is these two functions do cancel each other out, but they only cancel each other out if the number that you plug in right here is between certain values. Okay, and I'm going to show you how this works on the calculator. Okay, but it turns out in order for inverse sine and regular sine to cancel each other out, and basically all you end up with is this, okay, whatever's right there, it would come out as your answer. You have to start with a number that's between negative 90 and positive 90. Okay, or in radians, negative pi over 2 to pi over 2. Right, so let me show you an example on the calculator. Okay, let me type in the inverse sine of the sine of, and I'll pick a number between negative 90 and 90, 48. Right, now, when I hit enter, because I picked a value between the two that I said you had to be between, let's see, the inverse sine and the regular sine will cancel. And what should I get when I hit enter? Kyle?
Your x value?
Yeah, which in this case is?
48.
Yeah, which in this case is 48. So I hit enter, and that's what I got. Okay, let's try it for another one. Let's do second inverse sine of the sine of negative 57. Okay, Brian, when I hit enter there, what should I get?
Negative 57.
Yeah, I get negative 57. Okay, so the inverse sine and regular sine basically wipe each other out, and you're left with what you started with, okay, whatever you plugged in. Okay, well, I said it only works between negative 90 and 90. Okay, somebody give me an angle that's not between negative 90 and 90.
91.
91, right on the edge. All right, so 91. If I plug that back in, you can see I do not get back the same answer I started with. Okay? You might be able to figure out a pattern if you do enough of these and see the answer you do get back. But the point is, I just want you to understand you don't get back what you started with. Okay. So, any questions on when inverse sine and regular sine cancel each other out? Maybe between those two numbers. What's the difference between formula 2a and 2b? They both use the exact same functions, but there's a pretty big difference. Yeah.
The inverse is in the parentheses.
Yeah, we've switched the order that we're doing them in. So now regular sine is on the outside, inverse is the one inside the parentheses. So again, these two things will still cancel each other out, but now it's not negative 90 to 90. Okay, it's not even close to that. It's between negative 1 and 1. And yesterday we talked a little bit about this negative 1 and 1. Okay, these two numbers come from how high and low this graph goes. Okay, did we look at that graph yesterday? Yeah. Okay, when as high as 1 and as low as negative 1. That's where this is coming from. Okay, so let's try it. Let's try the sine of the inverse sine, and I'll pick a number between negative 1 and 1. 0.67. Okay. Because I picked a number between negative 1 and 1, which is what I have to be between when sine is on the outside, these two things should cancel out. And when I hit enter, what would you expect that I get? Oh, Alyssa? Yeah, we're going to get 0.67. The answer that you get is whatever you started with, okay? Because those cancel out. Okay. John, can you give me a number not between -1 and 1?
2.
2. Right.
0.3.
2.3?
Yeah.
Okay. Now, when I hit enter, this time, I don't even get back something different. The calculator says I can't even do it. Okay? So, this formula does not work if you pick a number bigger than 1 or smaller than -1. Okay, so any questions when this formula works? All right, so kind of problems you'll see on the test. Okay, it could be something like this. This is a yes, no, or a true, false kind of question. Is the inverse sine of the sine of pi over 8 equal to pi over 8? All right, so first of all, I want to figure out which formula this one follows. Is it more formula 2a, or is this one formula 2b? Yeah, it's 2a because the inverse is on the outside. So my restriction in radians is -pi/2 to pi/2. If you're not good with fractions and radians, what could you do with pi/8 if you had to?
Convert it.
Yeah, what could you convert it to?
Degrees.
Yeah, you could change it to degrees and see, are you between -90 and 90? If you're good with radians, do it in radians. Okay, but I'll change it to degrees if that helps. It's 22.5 degrees. So, Skylar, if I take the inverse sine of the sine of 22.5 degrees, will it come out to 22.5 degrees?
Yeah.
Yeah. Okay. Inverse sine on the outside says you got to stick between -90 and 90. 22.5 is between those two numbers. So we just write yes. That would work. All right. Let's try this one. Okay. The inverse sine of the sine of 3 pi over 2. Okay, Sam, is this one formula 2a or 2b?
2a.
Yeah, again, it's the inverse on the outside. Okay, so that's 2a. And how about Dan? For formula 2a, what's my restriction in radians? Between what and what? Yeah, what do I have to be between?
Pi over 2 or -pi over 2.
Yeah, I got to be between -pi/2 up to pi over 2. So is triple pi/2 between those two numbers? No. If you triple pi/2, you're way past it. If that doesn't make sense, change it to degrees, and you'll see that it's 270. So Dan, is the inverse sine of the sine of 3 pi over 2 going to come out to 3 pi over 2? No. That one doesn't work. Okay, so there's a couple examples of formula 2a. Jake, how about this one? Is this one 2a or 2b?
B.
Yeah, how come it's 2b? What tells you that?
The inverse is on the inside.
Yeah, now you got the inverse on the inside. Okay, so Shakira, what's my restriction for this number in formula 2b?
-1 and 1.
-1 to 1. Am I between -1 and 1?
No.
No. Okay, so that won't work. In fact, if you type it in, you won't even get an answer. It'll just say error. Okay, and let's try this one. Inverse sine is on the outside, so it's formula 2b again. Okay, so we know what we have to be between. Okay, Jared, is that number in between the two numbers I got to be? Yep, so that works. And that's basically it. Okay, so any questions on doing that with sine and inverse sine, when they cancel each other and when they don't? Okay, the only other type of problem you might see is I could word it this way. I could say simplify, and then I could just put that. If I write simplify, don't write yes as the answer. That doesn't really help. So you need to simplify it. So in this case, I'd be looking for a number, which would be 0.6. Okay? So if it says simplify, write the number. Don't write yes. Okay? If it just says something like this, is the inverse sine of the sine of 0.6 equal to 0.6? There's a question mark or whatever. Then you can write true or yes. All right, so we've got basically the same type of deal for cosine and for tangent. Okay, so let's start with the one where inverse cosine is on the outside. Anybody remember from yesterday what we had to be between for inverse cosine? It wasn't negative 90 to 90, but something similar. Yep, go ahead, Katrina.
Was it 0 and 180?
Yeah. So we're seeing some of these same numbers we saw yesterday pop up again today. Okay, so this one, basically inverse cosine and regular cosine cancel. And your answer will be whatever you type in right here, as long as you pick a number between 0 and 180. Or between 0 and pi. All right, and the other formula, okay, all we're going to do again is switch it, put the inverse on the inside. And the restriction here has to do with how high and low that wave goes. So sine and cosine pretty much have the same wave pattern. So what's the highest that wave ever went? 1, and the lowest? Yeah, -1. Okay. So cosine and inverse cosine cancel when you have cosine on the outside, as long as x is between -1 and 1. Okay, so this time we'll just try 2 of them. Okay, Jesse, this first one, it's got regular cosine on the outside. So is that more like formula 4a or 4b?
4B.
Yeah, that one's going to be 4b. So I know what that number should be between. Okay, Paige, what's my restriction in formula 4b?
-1 and 1.
Yeah, you got to plug in a number between -1 and 1 for this to work. Okay, and Karen, did we plug in a number between what Paige just said? Yeah. Okay, so what would be the answer to this problem? What would you write?
0.95.
So this one is more of the yes-no type. Is this equal to this? Yeah, you just write yes. If it said simplify and the number wasn't on the other side, simplify, you got to write the number. Okay, any questions on that one? Okay, and I won't ask you to simplify one that you can't. Okay, so if it's one that wouldn't work, it won't be a simplified problem. Okay, and Alyssa, how about this one? Is the inverse cosine of the cosine of 210 going to equal 210?
It's more like 4A.
Yep, it's more like formula 4a. So is our argument fit what it should be between? No, this one does not work. Okay, so any questions on those two formulas? You don't need to know that they're called 4a and 4b, and that's just what your book calls them. So if you want to look them up in the book, that's what they call them. But I'm not going to ask you something like that on a test. All right. And let's look at the last two for tangent. Okay, so the first one, we got inverse on the outside, regular on the inside. Okay, Eric, do you remember what we had to be between for tangent? Yep, negative 90 to 90. But how is it different than sine? Because sine is also negative 90 to 90.
It can't be negative 90 or 90.
Perfect. It just can't equal them. Okay, so x has to be between negative 90 and 90, not equal to this time. Okay, and the second one, it's a little different. Okay, did I show you guys the graph of tangent yesterday? No, we didn't look at that. So this second restriction, you can basically figure out if you look at a picture of your function, the original, and you look at how high and low it goes. Okay, for sine and cosine, you get a nice wave. With tangent, you get something that looks more like this. So there's a pattern to it, but it's not connected. So how high and low does it look like this graph is going? Yeah, it is going to go up and down forever. If you zoom out, okay, it should be going up and down forever, but clearly the calculator is having a little trouble sketching it. That's why sometimes when you depend on the picture on the calculator, it's not always accurate. Okay, so one way I can show you that it really is going up forever is, let me type in a number, okay, and I'll show you what happens. Okay, I'm in degrees. So if I try to type in 90, I don't get anything for y. Okay, if you look at your table, look at the tangent of 90, it'll say undefined. There's no y value if I pick 90. But let me pick something extremely close. 89.99. Look at my y value. 5,729. I'd say that's pretty high. So as I get very, very, very close to 90, this graph is shooting up very, very high. And if you go just past 90, okay, on the other side, it's going to go down very, very low. Try something like 90.001. Okay. Negative 57,000. Okay, so that's relatively low. Okay, so it is going up and down forever, which means on formula 6b, our restriction is between negative infinity to infinity. But what does that really mean?
It can be any number.
It can be any number. Yeah, so formula 6b always works. You don't even have to think about that one. Okay, it always works. All right, so let's try this one. This is example, I think we're at example 3. So is the tangent of the inverse tangent of 30.4, will that come out to 30.4? Yeah, how come?
Infinite?
Yeah, this is 6b. Inverse tangent on the inside, you can pick any number you want, including 30.4. So the answer here is yes. Okay, so that's the last thing they do in section 3.1. Any questions on that? Okay, not going to be a ton of questions about this on the test. Maybe, I think there's 2 at most. Okay, one of them is probably going to be a true/false. The other one, or a yes/no, and the other one will say simplify, and you'll just have to tell me the answer. Okay. All right. So our last section for this week is 4.1. Okay, we're skipping over the rest of chapter 3. Okay, we might come back to it at some point a little bit, but really the material in section 3.1 is directly related to what you do in 4.1. So it makes sense to do these 2 sections together. Okay, and we're going to talk about right triangle trigonometry. Okay, so some of you might have done this in geometry a little bit. If you've done the SOHCAHTOA, anybody done that? A few people? Okay. If you know what I'm talking about, then you've done things like this before. Okay, so first of all, everything we do in this section is based off of having a right triangle. Nick, can you tell me what does that mean? What's a right triangle?
It has a 90-degree angle.
Exactly. So a right triangle is a triangle with a 90-degree angle. And in a right triangle, we name the sides. Okay, the 2 short sides are called the legs, and the longest side is your hypotenuse. Now, what do all the angles in a triangle, bless you, have to add up to?
180.
Yep, they all have to add up to 180. And you've already used up 90 for that right angle. So what does that leave left for the other 2 together? Leaves a total of 90 left. And you have to split that between each of these angles. That means both of these angles have to be smaller than 90. Okay? Otherwise, the triangle would not add up to 180. Does anybody know the name for an angle that is smaller than 90? Yeah? Yeah, that's an acute angle. Okay, so it's smaller than 90, but it also has to be greater than 0. Okay, if you said is negative 10 degrees, is that an acute angle? No. It is less than 90, but it's not more than 0. And with what we're going to talk about this week, you'd never have angles that are negative anyway. It doesn't make sense. Okay, not for what we're doing. Okay, so we're going to come across some acute angles. And another theorem that's pretty helpful when we're dealing with right triangles is the Pythagorean Theorem. Can somebody explain or tell me what that is? What's the Pythagorean Theorem? About Marquise. You remember what that is?
A squared is NA plus B squared. No,
I think you're on the right track.
it was like C squared, something like that.
So a squared plus b squared equals c squared. So that's the formula. Can someone else tell me what's a, b, and c? Because I don't have any a, b's, and c's in my diagram. So I'm not sure what those letters are.
Your A and B are the legs, and then your C is the hypotenuse.
Correct. A and b are the legs. C is the hypotenuse. So the Pythagorean theorem is a relationship between the sides of a right triangle. Okay. It basically says that if you take one leg and square it, plus the other leg and square it, that's equal to the hypotenuse squared. Okay, you can call the sides A, B, C, X, Y, Z, call them whatever you want. But that's the important idea. Square one leg, square the other leg, add them up, and set it equal to your hypotenuse squared. So this theorem is going to be helpful if we want to figure out sides. Does this theorem have anything to do with angles? You think, no, this has nothing to do with angles at all. That's where trig would come in and help us out. Okay, but we can definitely use this to figure out sides. Okay, any questions on Pythagorean theorem? I'm not going to go through any examples that use it right now. We'll just, if we come across a problem where we need it, I'm going to assume everybody at this point has done it before. All right, so what we're going to do is we're going to define the 6 trig functions, just like we did for unit circle trig last week. Okay, we had sine, cosine, tangent, secant, cosecant, and cotangent. Now, last week the way we did it is we based everything off of a point on the unit circle. Okay, you had to have a coordinate. We're not doing that this week. Okay, we're going to use the terms opposite, adjacent, and hypotenuse. Okay, but first I just have to explain what those two terms mean. Okay, I think everybody knows hypotenuse. Okay, that's the side that's across from 90. But I want to explain opposite and adjacent. Hey, you know what? Before I even explain it, anybody tell me in this triangle where the opposite side is and where the adjacent side is based on what I drew? Sam?
Wait, are we going on the right angle or the angle you drew in?
You're always referencing the angle that's drawn like that.
Isn't the adjacent angle 90 degrees?
Not quite. So you might have to explain a little bit about what is opposite and adjacent referring to, sides or angles? Sides. Okay, so it's referring to sides. And Kyle, were you going to tell me anything more?
The adjacent is the one like right at the bottom.
That's adjacent,
Opposite is the top, like the left. Yeah.
and that's opposite. Okay, so opposite and adjacent are what we call relative terms. Okay, they can change depending on your perspective. Right? It's kind of like left and right. Left and right change depending on your perspective, which way you face. Right? If I say to reference this angle up here, right, pretend like you're standing right there. Okay, opposite is the side that's furthest away. Okay, so now that side is opposite. Adjacent is the side that's right next to. Okay, that's what adjacent means. Okay, like the table is adjacent to me. It's right next to me. Okay, so adjacent is the side that's right next to your angle. That's not the hypotenuse. Okay, another way you can describe it is if you took away the opposite side, it would not affect that angle at all. Okay, whatever angle is your reference point, you could take away the opposite side, and that angle would still be there. Okay, it's not part of the angle being referenced. Okay, adjacent is the side in the triangle that does, if you took it away, you'd wipe out your angle. Okay, if I got rid of this bottom side, I wouldn't have an angle right there anymore. Okay? So adjacent is the side in a triangle that forms one of the sides of the angle being referenced. And it's the side that's not the hypotenuse. Okay, you'll never do a trig problem from the perspective of the 90. Okay, we don't do it that way. It's always from the perspective of one of the acute angles. Okay, and I already explained what I mean by that earlier. They're relative terms, like left and right. Okay, something that's not a relative term is if I said north. I don't care which way you face. You can face the board, you face the wall, face the door. North is the same direction for all of us, no matter which way you're facing. Okay, like magnetic north. unlike left and right. That changes. Okay, so any questions on what I mean by opposite, adjacent, or hypotenuse? All right, so now that we've got those two terms hopefully clarified, we can define our 6 trig functions. Okay, and rather than me going through them, I'm going to ask some people, if you've had geometry, you might remember it. Does anybody remember what sine is? It's a fraction. And all of them use the words opposite, adjacent, and hypotenuse. They all use 2 out of 3. Yeah?
Sine is adjacent over hypotenuse.
Adjacent over hypotenuse? That one's going to be cosine. But we're on the right track. So that one was cosine. So what's sine? Yeah?
Opposite over hypotenuse.
Yep, sine is opposite over hypotenuse. And does anybody know tangent? Dan?
Opposite over adjacent.
Yeah, it's opposite over adjacent. Okay, so now we're not depending on having a coordinate anymore. Okay, we're not using a coordinate on the unit circle. We're dependent on knowing all the sides in a triangle. Okay, does everyone have what's on the left so I can make what's on the right bigger? Okay. Now, last week, we did something to the 3 on the left in order to get the 3 on the right. Does anyone remember what we had to do to each one of these to get the other 3? Shakira? We flip them. So what do you think the cosecant would be?
Hypotenuse over opposite.
Yeah, hypotenuse over opposite. All right, Kate, how about my secant?
Hypotenuse over adjacent.
Yep, very good. Hypotenuse over adjacent, and cotangent is adjacent over opposite. Okay, so it might seem different than what we did last week. We had sine was y, cosine was x, tangent was y over x. But this is exactly the same thing. It's a different way of looking at it. I'm not going to make the connection right now, but it is the same thing. All right, and there's a trick you can use to try to remember at least the 3 on the left. Okay, and that's this. Okay, Sakatoa. Okay, I've had people before suggest try to use Sacagawea. It's not Sacagawea, that won't help you. But Sakatoa, that'll help you try to remember it. Okay, did anybody tell me what that stands for? You know, Jesse?
So is sine, and then it's opposite over hypotenuse.
Yeah, sine is opposite over hypotenuse. Yep.
And then the cohort is cosine, and it's adjacent over hypotenuse.
So cosine is adjacent over hypotenuse. And what about the last part?
Tangent is opposite over adjacent.
Yeah, tangent is opposite over adjacent. Great, so reading down, that'll help you. Don't read across, that doesn't really make sense. Ipiodepada. This is not going to help. So read down. And then if you can just remember the first 3, then all you got to do is flip those 3 to get the next 3. In general, we're not going to be using these 3 too much. Okay, we're going to stick mostly with sine, cosine, and tangent, especially for everything we do tomorrow and on. Okay, but we'll practice with these other 3 a little bit. Okay, everybody have those definitions written down? All right. So, they're giving us a triangle, and they want us to find all 6 trig functions of theta. Okay, so this symbol here, a circle with a line to it, it's theta. So everything is from the perspective of theta. Pretend you're standing at theta. That should tell you which side is opposite, which side is adjacent. So what am I missing here? I'm missing something that I'm going to need, at least for some of these trig functions. I don't need it for all of them, but I need the hypotenuse. Okay? Sine uses it, so does cosine, cosecant, and secant. So I can't do the top four until I find the hypotenuse. Okay, so Claire, how do I find the hypotenuse if I know these two sides?
Because those two sides are the lengths.
Yep.
So plus 9 degrees on top.
So how do you get this side?
Since you already know those are lengths, so it's just, I don't know, it's not figured out.
So how long is it? I want to know exactly. Is it like 6 units, 7 units? How do I get exactly how long it is?
I don't know.
Not sure. Anyone help her out? Something I mentioned earlier today. Katrina?
Pythagorean.
Or just, yeah?
Pythagorean Theorem.
Yeah, we just do the Pythagorean Theorem. Okay, so find out how long this side is. If it comes out to a square root, I'll talk about that in a second. If it doesn't, that would be nice. But a lot of times it does come out to a square root. Okay, so 3 squared plus 4 squared. If you want to call that side C, that's fine, C squared.
Did you just plug in the 4 and the 3?
Yep, I just plugged in each leg into the Pythagorean Theorem. Yep. And now I'll square them and add them up. So that's 9 plus 16. What's 9 plus 16? Good, 25. And now I want to get rid of this exponent of 2. So what do I have to do on each side? Yep, take our square root. So how long is the hypotenuse? 5. Okay, so this time it came out nice. If it doesn't, and it comes out to a square root, like let's say you got, I don't know, square root 12 is the answer. Okay, 2 things. One, you always have to reduce it as much as you can, okay, just like we did first week of class. And 2, if it ever ends up in the bottom of a fraction, you need to fix it. Okay, just like we did with unit circle trig. This problem is going to work out nice, okay, because 5 is not a square root. Okay, so I'm just saying if you had something like this, you got to simplify and don't leave it in the bottom. All right, so let's start with our sine. How about Shannon? What's my definition for sine? It's what divided by what?
Opposite of the hypotenuse.
Opposite of a hypotenuse. Okay, what's the opposite in this case?
4.
4? And the hypotenuse?
5.
5. That's it. Okay, so the sine is 4/5. Okay, Selenia, how about the cosine?
Adjacent and hypotenuse.
Yeah, adjacent over hypotenuse. So in this case, what would I get?
3/5.
Good, 3/5. And Rebecca, the last one, what would be my tangent?
4 over here.
Yeah, perfect. Okay, opposite 4, adjacent 3. And that's it. All right, and now Skylar, to get the 3 on the left, or on the right, what do I do with the 3 on the left? Yeah, just flip each one. Okay, so cosecant is 5/4. Secant is 5/3. And cotangent, 3/4. Now in this problem, I figured out a lot of different things. I figured out the hypotenuse, and I figured out all 6 of these trig functions. Anybody see something that I didn't figure out in this problem? The what?
Angle.
The angle. I didn't find out how big this angle was. That part will be tomorrow. any one of these 6 pieces of information is enough for me to figure out the angle. Okay? But that we'll save for tomorrow. Any questions on that? Okay, so that's finding the 6 trig functions. All right, so last thing we're going to talk about ties really 2 ideas together. Okay? Complementary angles. Okay, we'll talk about what those are in a second, or hopefully review what those are. And what's called co-functions. Okay? You already know the co-functions. I've just never told you that they're called co-functions. Okay, so I'll show you what those are after complementary angles. Okay. Anyone remember from geometry what it means to have complementary angles? Yep, Kyle?
The 2 angles that add up to 90.
Yeah, it's 2 angles that add up to 90 degrees. So complementary angles are 2 angles that add up to 90. And I'm saying here that the 2 acute angles in a right triangle are always complementary. Why? Why would if you draw a right triangle, why does this angle and that angle always have to be complementary? Eric?
Because there's already 90 degrees and there's only 180 degrees in a right triangle.
Okay, so we've used up 90 degrees here. There's only 180 in a right triangle. So
180 minus 90 is 90.
So that leaves 90 left for the other 2. Okay. Does anyone need me to write that out? Okay, so triangle has 180. You use up 90 for the right. You got 90 left for the other 2. That forces them to be complementary. Okay, so that's the idea of complementary angles. Okay, the next thing is cofunctions. Okay, cofunctions are a different way to pair up your trig functions. Okay, this pairing that I have here, where you flip one to get the other, these are called reciprocals. Okay, flip sine, you get cosecant. Flip cosine, you get secant, and so on. Okay, so these are paired up as reciprocals. Okay, if you want to pair them up as cofunctions, you pick a trig function, and then you pair it up with the trig function that has the same name except the word co in front of it. Okay, so we have sine. Its cofunction is when you put the word co in front of what I just said. Cosine. Okay, sine, cosine are called cofunctions. What function would be paired up with secant? Co-secant. Secant, cosecant. Those are called cofunctions. And lastly, what function would I pair up with tangent? Cotangent. That's actually the same pairing we did before. Okay, it's the only one that is the same. Okay, so these are your cofunctions, those 3 pairs. All right, so now I'm going to make a sketch. Okay, I'm going to draw something out and see if we can see a connection between these 2 ideas. And that's going to lead us to the last thing, which is the complementary angle theorem. All right. So what I've drawn here is just a generic right triangle. And I think everyone's pretty familiar with labeling the sides. Okay, usually you use A, B, and C. But how about these other 2 letters? Does anybody know what these 2 letters are? Or how about even more general? What alphabet are they from? Yeah, they're from the Greek alphabet. And yeah, the top one is beta. And how about the bottom one? It's the first letter in the Greek alphabet. What is it? Alpha. Yep. So when we label a right triangle just generically, you always put A across from alpha, and you always put B across from beta. And C would always be the hypotenuse. I'm not going to use, yeah, I might use C. So it's a good idea to label C. You don't need to label this angle because it's always the right angle. Okay, so you don't need a name for that. All right, let's look at a few trig ratios here. Let's look at the sine of alpha. Okay, so sine is opposite over hypotenuse. Nolan, what side is opposite alpha? A. And sine is opposite over hypotenuse. What's the hypotenuse here? C. Okay, so sine of alpha equals A over C. Nothing very interesting there. But let's look at something a little different. What's the cofunction of sine? Cosine. And what's the complement of alpha? What's the angle that you would add to alpha to get 90? Beta. Okay? So I'm doing two things. I'm looking at the cofunction of the angle I started with and the complement of the angle I started with. So cosine is adjacent over hypotenuse. Right, so Kate, what side is adjacent to beta? A, yeah. A is right next to it. And how about John? What side is the hypotenuse again?
C.
C. What do you notice about the sine of alpha and the cosine of beta? Came out exactly the same. Okay. Let's do one more and just see if that was a coincidence or if that always happens. Okay. Tangent of alpha. Okay. Tangent is opposite over adjacent. So Sam, what side is opposite alpha here? A. And what side is adjacent? B. Okay, so that's A over B. Now I'm going to change it. I'm going to look at something a little different. I'm going to look at the cofunction. Alyssa, what's the cofunction for tangent?
Okay. Wait, no, what?
The cofunction for tangent.
Oh, it's
Sure. Well, yeah, cotangent. Yeah. And we already said earlier, what angle is the complement of alpha? What, Jake? Beta. Okay, so let's find this. It's the cofunction and the complement of the original. Cofunction, complement. Keep those two things in mind. Okay. Cotangent is adjacent over opposite. So from the perspective of beta, adjacent is A. What side is opposite? What side's furthest away? B. What do you notice about these two things again? They're about the same, right? And that's always going to happen as long as you have cofunctions and complements. Okay? And that's called the complementary angle theorem. Okay? It says exactly what we just figured out. If you have cofunctions of complementary angles, they come out the same. Always. Okay, so we'll finish up with a problem where you would see something like this. All right, so if I asked you for something that was the same as the sine of 30, okay, you have to think of two things. One, what's the cofunction of the one that I listed? And two, what's the complement of the angle that I listed? Okay, so let's start with sine 30. What's the cofunction for sine? Cosine. And what's the complement of 30? 60. Right? 30 plus 60 adds up to 90. So what that means is if you've got cofunctions and angles that are complementary, they will come out exactly the same. And you could double check it. If you type in sine 30, type in cosine 60, you get the same thing. Okay, how about the next one? Tangent of 15 degrees. What would that be the same as? Yep, Jasenia?
Is it cotangent 75?
Perfect. Yep. So she picked the cofunction, and she picked the angle that adds to what I was given to get 90, the complement. And how about the last one? Secant of 40. Sam? It's the cosecant of 50. Yep. Okay, so knowing those things come out the same should allow us to answer this question pretty quickly. Okay, so I've set this up in a very special way. Sine and cosine, those are your cofunctions. 15 and 75 are complements. So anybody think they know what you're going to get if you divide those two things? Not sure?
You're going to get 1 because they're the same.
Can you explain that? Why do you get 1?
Because they're the same, they have the same value if you calculate it out.
Right. The sine of 15 is exactly the same as the cosine of 75. These two things are equal. I have no idea what the sine of 15 is. I don't. It's some weird number. Okay? And I don't know what the cosine of 75 is. But what I do know is it's the same weird number. So if I divide two things that are the same, I know I'm going to get 1. Okay? This trick wouldn't work if you change this 15 to a 16. These numbers have to add to give you 90. These have to be cofunctions. If that doesn't happen, the trick doesn't work. So it's a very, very special trick that only works in certain situations. Okay, how about this one? Tangent of 12 minus cotangent of 78. Right. Can you explain why it's 0? Go ahead.
Because they add up to 90 degrees.
Okay, the angles add up to 90. Yep.
A number minus itself is 0.
How do you know these are equal, though?
Because the angles add up to 90 degrees. So they're,
Well, that's the first part. What else has to happen?
They have to be cofunctions.
Yeah, they have to be cofunctions. Like if I did sine of 12 minus cotangent 78, that doesn't work at all. Okay? This and this are exactly the same thing. Again, I have no idea what the tangent of 12 is. It's some long decimal. Same with cotangent 78. But what I do know is that they're the same. Subtract two things that are the same, you get 0. So this works with division. It works with subtraction. How about addition? If you add two things that are the same, do you always get the same answer? No. You get that thing doubled. Okay, you don't get the same thing though all the time. How about if you multiply two things that are the same? No, you get that thing squared. All right? So this trick only works with subtraction and it only works with division. And that's it. Okay, so that's the complementary angle theorem. All right, so the first part of the homework, these are all just yes/no questions. Okay, on page 187. Or true, false, however you want to say it. So page 187, 46 to 51, 53 to 55 all. And then on 255, that gets into the stuff that we did with right triangles, Pythagorean Theorem, and the 6 trig functions. Okay, so on 255, just 9 to 21, odd.